Here we have another recipe to calculate the residue of a single pole. Just write your whole function as this fraction over here. Take the derivative of the denominator, plug in z0 everywhere, and then you have your residue. The question is, can you prove this particular formula? So let's pause the video and try and figure this one out. Perhaps a little hint first is in order. So we have our function f of z written as a fraction, like so. Now, if we know that z0 is a single pole of this function, it means that z0 will also be a single zero of our denominator over here. So we can factor this thing out, and we can write that explicitly as z minus z0 times some sort of a remainder function, which we will be calling r of c. So now that we've written this thing in the following form, then perhaps it's a good idea now to apply the formula that you already know to calculate the residue and see if you can prove what needs to be proven here. So let's just pause again and work this thing out. So what is the recipe that we know to calculate the residue? Well, we know that the residue at a single pole can be calculated by taking our function, which by now takes this slightly scary looking form here, z minus z0 r z, taking our function, multiplying it by z minus z0, and then evaluating the whole thing in z0. Now, the good news is, of course, that this thing cancels, and it becomes quite simply then the following expression, which is basically what we need to show, apart from a small detail here. So the numerator is fine, but for our denominator, we would like to show that this is equal to the derivative of h at z0. So we have a small little thing to prove, but once we have that, then we're basically in business. However, that's fairly trivial here. So we know that we can write h of z as z minus z0 times this remainder function. And then we just calculate the derivative. First of all, the derivative of the first factor, that's just 1. And then we keep the second factor. And we keep the first factor. And we take the derivative of the second one. And here, quite trivially, if you now insert z0 into that equation, this whole stuff over here will vanish. And we have indeed shown that r of z0 is equal to h prime of z0. So we're in business here. Personally, I prefer this recipe to calculate the residue of single poles, because otherwise you will need to explicitly factor out this z minus z0. Here, just taking a derivative of the denominator is typically much faster. So if you like to be lazy / efficient like me, I would suggest that you use this particular formula to calculate the residues of single poles.